So in this lecture we're going to cover this concept of expanded octet. Or compounds that violate the octet rule. Okay, so if we take two compounds, NCl5 and PCl5, for example. So NCl5 does not exist, whereas PCl5 exists. It's a real molecule that you could synthesize in lab if you wanted to, or you can buy it. So if you notice, both phosphorus and nitrogen are both in group 5, so why does PCl5 exist but NCl5 does not? So if we drew a Lewis dot structure for both of them, so nitrogen's got 5 valence electrons, chlorine's got 7, and there's 5 chlorines, so that would be, oh boy, 35 electrons. Did I do that right? I did my math wrong. No, that'd be 40 electrons. There we go. And so same for PCl5, phosphorus, 5 valence electrons, chlorine, 7 times 5, that would be 40 electrons. So if we drew a Lewis dot structure the way that we've been drawing them in the past, if you put nitrogen in the middle and attach the 5 chlorines, or phosphorus in the middle, and then add lone pair electrons. So give each chlorine 3 lone pairs, and then they have 8 valence electrons. And same for PCl5. Okay, and then what would we do next is we would count our electrons, right? So we have 1, 2, 3 times 5, or 3 lone, yeah, 1, 2, 3 lone pairs on chlorine times 5 chlorines, that would be 15 lone pair. That would equal 30 electrons. And then 1, 2, 3, 4, 5 bonds. That would equal 10 more electrons, so that would be 40 electrons. So they both have 40 electrons, so we have the right number of atoms, we have the right number of electrons, but one of these exists and one does not exist. So what's wrong with this Lewis structure, based on what we've covered in the past, is that violates the octet rule on nitrogen, right? Good, you have 10 electrons on nitrogen, and that is not okay. Whereas 10 electrons on phosphorus is okay. So what's the difference? Why can phosphorus have 10 electrons around it in its valence shell, but nitrogen cannot? And the difference is, so nitrogen, so if you remember, this is 1s1, 1s2, so this would be 2s1, 2s2, and then through here would be 2p1 through 2p6, so nitrogen would be 2p3. So electron configuration for nitrogen, 1s2, 2s2, 2p3. And so if you remember, this is its valence shell. So it's got 5 valence electrons. And to complete its valence shell, it needs 3 more electrons to become 2s2, 2p6, and then that would be that would be 8 electrons. And that's the basis of the octet rule. If you complete its outer shell, then it looks like a noble gas and it has 8 valence electrons. So nitrogen can only have 8 electrons in its valence shell. Whereas if we go to phosphorus, so then this would be 3s1 and 3s2 for sodium and magnesium. And then for phosphorus, it's 3s1 through 3p6, and it's 3p1 through 3p6, and it's outer shell. So nitrogen's valence, so nitrogen's or phosphorus's electron configurations: 1s2, 2s2, 2p6, 3s2, 3p3. So if we complete phosphorus's valence shell, how many more electrons can the third shell hold? And the answer is not 3 like a nitrogen, because if you remember, third shell also has d orbitals. So nitrogen or phosphorus's valence shell 3s2, 3p3, but it also has 3d orbitals which have 0 electrons in them. So if you finish phosphorus's valence shell, it could hold a total of 3 more electrons here and 10 more electrons here. So it could have 13 more electrons. Or total, third shell with the 3s2, 3p6, 3d10, it could have a total of 18 electrons in its valence shell. So basically, any atom in third period or below can have what's known as an expanded octet. Can hold up to 18 electrons instead of 8 electrons. So for PCl5 then, okay for phosphorus to have 10 electrons. So that would be the reason why PCl5 can exist and NCl5 cannot exist, because PCl5, since it has empty d orbitals, it can accommodate more electrons, and it's okay to put more than 10 electrons around it. So let's take a couple more examples. So SO4 2-, for example, and IF5. So let's draw Lewis dot structures for those compounds. So sulfur has 6 valence electrons, oxygen has 6, and there's 4 of them. How do we know it has 6? Because if you go back to the periodic table, it's in group 6. So it can have 6 valence electrons. And then what do we do with the 2 negative? That means we add 2 more electrons, so that would be 32 electrons. And for IF5, iodine has 7 valence electrons, fluorine has 7 valence electrons. So we need 42 electrons for IF5. Okay, so for SO4, so if we drew a Lewis structure, so if we put sulfur in the middle, attach the 4 oxygens, and then give everything enough lone pairs to make 8 to complete the octet. So then now that would be 1, 2, 3 lone pairs on 1 oxygen. There's 4 oxygens, so that's 12 lone pair. So that equals 24 electrons, and 4 bonds equals 80 electrons, so that's 32 electrons. So that's the right number of electrons. Sulfur has 4 bonds, so 8 electrons, so its octet rule is filled. Oxygen has 8 electrons, so its octet rule is filled. So that's an okay structure for SO4 2-, but sometimes you would see SO4 2- drawn like this instead. And so in this case, sulfur has 1, 2, 3, 4, 5, 6 bonds. So 12 electrons. And is that okay? So it's got an expanded octet, and it is okay because sulfur is a third period element. So basically any element in the third period or below can have an expanded octet, because in the third period you have d orbitals. Once you get to the fourth period, then you also have f orbitals, so they can have even more electrons around them. So this is a perfectly fine structure for SO4 2- as well. So now which is better, the one on the left and the one on the right? And if you remember how to determine that, you had to assign 4 more charges. So if we assign 4 more charges for this oxygen, 6 valence minus 6 dots minus 1 line is -1. So that oxygen's -1, that's -1, that's -1, that's -1, because all 4 oxygens look the same, 3 lone pairs and 1 bond. And then if we did the same for sulfur, so 6 valence electrons minus 0 dots minus 4 lines, it would have to be +2 charged. And then for the other structure, so sulfur, 6 valence electrons minus 0 dots minus 6 bonds, it would have 0 charge. And oxygen, 6 valence minus 4 dots minus 2 lines equals 0 charge. So this oxygen's 0, this oxygen's 0, sulfur is 0, and this oxygen, 6 valence minus 6 dots minus 1 line is -1. So that would be -1. And that oxygen looks identical, 3 lone pairs and 1 bond, so it would be -1. So based on that, which structure is better? Well, if you remember, the one that has the minimal 4 more charges is a better structure. So the structure on the right is better structure, and so that's why SO4 2- would typically be drawn like that. And so if you notice again, the sum of 4 more charges is 2 negatives, so that would be a net. Okay, and then for IF5, we said it has 42 electrons. So if we put iodine in the middle and attach the 5 fluorines, and then give each fluorine 3 lone pairs to complete its octet. So fluorine's a second period element, right? So it can only have 80 electrons. So second period elements, you cannot violate the octet rule on them. They can have a maximum of 80 electrons around them. And so we give each fluorine 3 lone pairs. So that would be 3 lone pairs on each fluorine times 5, that's 15 lone pairs. That equals 30 electrons. And iodine, 5 bonds, that would equal 10 electrons, so that's 40 electrons. But we're supposed to have 42. So we need 2 more electrons. Where do they go? So can we put them on, so maybe could we do something like this? Could we add a double bond? So that would be 2 more electrons, so that would be 42 electrons. But we can't do that, right? Because that would violate the octet rule on fluorine, so we can't do that. So let's get rid of that. We can't add a lone pair to any of the fluorines because that would violate the octet rule on fluorine, but we can do is simply add a lone pair to iodine, and so now that's 42 electrons. And iodine has, so 5 bonds, 10 electrons plus 2 a lone pair, so that's 12 electrons. Is this okay? Well, you got to see where iodine is in the periodic table. So iodine is here. It's in the 2nd, 3rd, 4th, 5th period. So yes, iodine can have an expanded octet because it has D and F orbitals, so this is okay. So then that's the structure. So fluorines each have an octet. It's 42 electrons. Iodine can have an expanded octet, so that's a good structure. That's what IF5 looks like. Okay, so lastly, in this lecture, let me just say a little bit about bond strength. So the carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. If you look at the bond strength, so carbon-carbon single bond is 348 kilojoules per mole. That's how much energy would be required to break that bond. Double bond is 614 kilojoules per mole, and a triple bond between two carbons is 839 kilojoules per mole. So the basic point is, in terms of bond strength, triple bonds in general are stronger than double bonds, which are stronger than single bonds. So it doesn't matter what the compound is, triple bonds are stronger than double bonds, which are stronger than single bonds. Okay.